All right, it's 2:15. I'll let us get started. I don't want to cut into your time here while you present. So really quick, this is Aaron Perkins. He's with Buildertrend, and he's going to be your presenter today. I'm going to hop off and leave it to him to get going for this breakout session.
Thanks, Emily. So yeah, the presentation today is Edge Computing with .NET Core and Raspberry Pi. My name is Aaron Perkins. So who is this guy talking? I've been in software development for about 20 years. I'm currently a senior engineer at Buildertrend, a leading construction management software company. And I really have a passion for bringing people and technology together to solve problems, which can be a struggle sometimes because, to pay the bills, sometimes you're doing pretty abstract work. You're working on back-end processing, number crunching, integrations, other kind of boring applications. I'm sure if you're in application development, you've all been there. Often your applications are deployed to the cloud, so you never even physically see where your application is deployed. But what really gets me excited are applications that directly impact people in the real world. Something that has a real world presence, something you can actually reach out and touch, measures the world and interacts with the real world. That's why I tend to enjoy hardware-based projects, and kind of that's what brings me to edge computing and Raspberry Pi and those kind of technologies. So this presentation will kind of go through a brief introduction of what edge computing is, a few slides, and then we'll get to a demo of what it's like to work with Raspberry Pi and .NET Core and how you can apply this to solve problems. There'll be some time at the end to ask questions. I'm more than happy to. So what is edge computing anyway? It's one of those buzzwords that's not really easily definable, but hopefully I can help with that. First thing though is it's definitely has nothing to do with Microsoft Edge browser, thankfully. If you've Googled Edge computing, you might have come up with a diagram that looks something like that. That's where I found this diagram. The general idea is that there is a top layer where your centralized applications mostly hosted, in a cloud or a data center or some hybrid of the two. And then on the bottom here, you have your Internet of Things. Here's another buzzword. What's IoT? To me, an IoT device is simply a device that's connected to the internet that sends information back to your application over the internet. Things like smart thermostats or hardware that monitors the power grid or factory equipment, or something that's not on this diagram is really your smartphone, for example, is an IoT device connected to the internet, and if it's interacting with your company's product, that's an IoT device interacting with your system. So you have your IoT devices all collecting data and interacting with your centralized application. And then the edge is this middle layer here, sometimes called the fog, I guess because it's on the edge of the cloud. To me, I call it the fog because I really don't have the foggiest idea of what this is supposed to be and when most people talk about it. It doesn't really make sense. Are these servers that are close to, in the car, or how do you have a server that's moving or out in the middle of a field and nowhere, for example, next to the power lines? Where are these servers? Where are they physically, and what are they exactly? So I like to simplify the definition a little bit on what edge computing is. For me, it really boils down to this. It's computing physically close as possible to your application's user and data by leveraging the cheap, powerful, and portable platforms available today. So let's dissect that a little bit. What do I mean by compute close to your users and data? Really what it comes down to is latency. If you think of a traditional web application that's talking to your server, your users are using their browser and they click a button and that information has to travel from the browser to the server and then back again across the internet, which is a delay factor. And most users like me want a fast, responsive application. So anything you can do to minimize that delay makes your application have a better user experience. You can think of other use cases, for example, high frequency trading. These companies that do this kind of work, they pay massive amounts of money to co-locate their servers as close to the trading platform as possible so that their trades can operate as quickly as possible. So you can think of this, those are two different scenarios where you want your processing close to either the data that it's processing on or your end users. The other important aspect of this is offloading workload. So if you think of a smartphone as a very powerful device, your desktop is a very powerful device with your browser. Why not use some of that computing power to make your application more responsive and a better user experience? So latency, offloading workload are two reasons why you want to get close to your users. The second half of this sentence is cheap, powerful, and portable. So this will be about the Raspberry Pi, which is a platform that's so cheap that the Raspberry Pi Zero was the first full computer to be given away with a magazine subscription, which is kind of crazy. You get a full computer when you subscribe to a magazine. It's powerful enough to run a full modern desktop experience with a web browser and all that. And it's small enough that it was actually glued on the inside cover of that magazine is how they actually gave it out to their subscribers. So great, we've defined what edge computing is. How do we actually apply it to a real problem? So I like to use the scenario of you're working for a weather data providing company. So a company that basically provides data about the weather, forecasting models, those kind of things. You might have a bunch of devices out in the field, all collecting different weather data. For example, temperature, pressure, humidity, those kind of things. Sending all those data points back to your centralized application that's running a forecasting weather model. Those are very compute intensive activities. They need to be continuously updated with real time with data that's being fed in. So you might be a developer working there, everything's going great. And then one day your boss comes over or maybe calls you virtually in today's climate and says something like, hey, we got 10,000 weather stations out there sending us millions of data points a second. We can't process this data fast enough. Our server guys are throwing more hardware at it, but they're at their wits' end. They're going to quit. We need to figure something out, and I need you to maybe work a weekend shift or something here to figure this out. Hopefully you haven't been in a situation, but you can imagine this situation happening. Traditional solution to this problem is, again, throw more hardware at it. Either if you have a data center, buy more servers, or if you have a cloud service, rent more resources, more VMs as a problem. It's a solution, but it's expensive to scale, and it does have limitations eventually. What if instead you could offload some of this processing to the devices actually collecting the data? So instead of the devices being just dumb sensors that send temperature, humidity, pressure to your backend application, they're running some localized version of your forecasting model, doing some of that number crunching on the device itself. So maybe instead of having a million data points a second, maybe we can get that down to tens of thousands of million data points a second, because some of the processing power has been offloaded to these edge devices that are collecting the data. This is kind of an ongoing trend that's been happening in the software industry since even before I started it. You think of like how architecture and applications are moving from monolithic to microservice, where we're distributing the computation across multiple services instead of having one big service. And now it's really moving into multiple platforms. So let's distribute the application instead of having all centralized in one data center. Let's distribute the application to all the devices impacted by or used within the application. So, we have kind of the problem defined. We have a strategy of how we want to approach the problem, which is, distributing the workload across mobile devices. Let's talk about what that solution might look like, and specifically what kind of platform that we'd be starting with. And of course, my favorite platform is the Raspberry Pi. Not that Raspberry Pi, even though it's delicious. I'm talking about this Raspberry Pi. What is the Raspberry Pi? If you don't know, it was invented by a man named Eben Upton in 2012, and he was really interested in getting children interested in computing by giving them a hardware device that was cheap, cheap enough that you can give to a kid and not worry if they break it, basically. And it kind of ballooned from there. The maker community really got onto it, and big companies started jumping onto it. It became a very popular platform. It's based off of a ARM SoC designed originally for smartphones. And kind of that was the genius of it, is economies of scale. If you build a platform based off of smartphone technology, there's lots of manufacturers making that hardware, so you can leverage those economies of scale to get a really cheap price. They range in lots of different models, from $5 to $55. The top of the line models have a quad cores, USB 3, Wi-Fi, 4K output. The lesser models, less so, but they're cheaper. You have to pick the one that really matches up for you. But there's a lot of different models out there. Basically, a model to fit what your use case would be in a particular scenario. There's been over 30 million of these sold across the world. I've bought my fair share, probably more than my fair share. I currently have probably about 25 Raspberry Pis floating around my home, doing like home automation tasks, or media centers, or I think I have one that runs my 3D printer that I use. When a new Raspberry model comes out, I'm usually the first one to buy it. It's kind of a little bit of an addiction, unfortunately for me, but moving on. They also have hats. Not really these kind of hats. They have these kind of hats. These stand for hardware attached on top. And these are pieces of hardware that you can put on top of the Raspberry Pi to expand its functionality. They have lots of different uses. There's sensor arrays, there's displays, cameras, AI accelerators. There's this hat, which I'm really not sure what it does, but it looks really cool. You can even do things like put other Raspberry Pis on top of your Raspberry Pi if you want. I'm not sure why you would do this, but I'm definitely going to try it out because it looks really cool. Oh, and by the way, Raspberry Pis work really great with .NET Core. They also work great with Python and Java and all those kind of things, but I've been a .NET Core developer, so it's really important to me. Microsoft really threw their support behind the platform. The Raspberry Pi can run Windows 10 or Linux. .NET Core runs on either platform. Linux is generally the more supported one. The community really got behind the Linux distribution, including Microsoft. So most of the tooling and everything is really about the Linux distribution. You can even run full .NET framework on a Raspberry Pi through Mono, for example, if you want. But .NET Core runs really well on the platform as far as speed and stability and tooling support. It's really kind of a first class. Microsoft made the Raspberry Pi a first class platform for .NET Core. And the great thing about Raspberry Pi is it kind of combines high-level languages like .NET Core with the ability to work with the embedded world. So kind of an embedded computing 101 here. The Raspberry Pi has a 40-pin header that's available on every Raspberry Pi, and this breaks out a series of communication pins that are available for your hardware projects. A lot of embedded hardware, doesn't use USB or more kind of desktop or PC normal interfaces. They use these lower level ones. So a quick run through of what the different options are. In orange here, you have GPIO, general purpose input output. You can think of this as an on-off switch. So you can either read an on-off value or write an on-off value to any number one of these orange pins. and you can do it really fast, like millions of times a second. It's just really useful for doing simple things like turning a light on and off, or more complex things like running a serial interface connection across it. It's kind of the Swiss Army knife of embedded electronics. The Raspberry Pi also has a SPI, single peripheral interface. This is a interface that came out of I think Sharp made it in the 1980s, but basically it's a way for two electronic components to talk to each other, whether it be two chips on the same board or maybe two boards to connect to each other. It's high bandwidth, like 10 megabits a second. It needs a lot of wires. It's really only good for short distances. And the one we'll be focusing on more today is the I2C or integrated circuit communication. So that's the teal pins here. Some great things about I2C is you only need 2 wires. It's a bus mechanism, so you can talk to any number of other components. Again, with those only 2 wires. It works on longer distances, and it is a little bit slower. We're talking like speeds of like 100 kilobits per second kind of communication rates. But for reading sensor information, those kind of things, works great, which is exactly what we'll be using it for. Oh yeah, it uses a master slave. I tend to like say leader follower instead, just to kind of, I just think that's better terminology. So enough talk, more code. I'll have a link to my GitHub, so all the code you're going to see is on a GitHub page that you can go look at your convenience. I'll make sure you guys have a link to that before I leave. But what we're going to be looking at is a weather station application that has been written to run on a Raspberry Pi. So I have my Raspberry Pi right here, actually. Try to get to the close enough to the camera so you guys can see it. So it's a Raspberry Pi 4, which is way more powerful than we need for this application. But I just want to have it available to me. And then there is a hat on it, which is a Sense hat, which is some random sensor hat that I got off Amazon for like $10. And it has a bunch of different sensors on it, including temperature, humidity, and like a gyroscope and some other things on there. And then it's just I just have it attached to a power battery here that's used to charge your phone, just so it's completely portable. We'll be connecting to it over Wi-Fi, and it's basically going to be hosting a web application that's done in React and .NET Core that we can access over that Wi-Fi connection. So let me switch it over here with to my Visual Studio Core. I'm sorry, Visual Studio Code. That's what I meant. Okay, so this is basically I use the .NET tool to basically create a React application. This is just the default React application you get. Then I added onto it to add the functionality I need. So in the client app folder, we have just a traditional React application. You can see there's a weather component that basically represents this UI over here. And you can see that every second it calls this populate weather data function, and it makes an internal fetch to an API, to a Git API that basically pulls back the weather and then populates this internal state, updating this UI. Kind of moving down the stack, so I'll move down the stack from UI to, now here's the controller. The controller takes those API requests and calls a sensor class that gets a reading and returns the result. And then, so one of the things that one of the strategies I like to do when I'm working with embedded projects is fake out the hardware at first. The Raspberry Pi is a great platform, has a lot of uses, And you can even run Visual Studio Code on your Raspberry Pi and do all your development on the Raspberry Pi, but it's not the fastest development environment. It's nowhere near as fast as my desktop computer I'm using right now. So especially when you're doing development that might not even relate to the Raspberry Pi, like you're trying to get your UI to look the way you want to look, and you're trying to get your basic project set up, it's just so much faster to work on a desktop. So I want to be able to use my desktop to write the code and then even debug it on the Raspberry Pi, which is what I'll show you. But before I even connect it to the Raspberry Pi, I'm doing the development. One strategy is to interface out the aspects that require to actually be on the Raspberry Pi. So in this case, I created an interface called iWeatherSensor. And then when I'm working with this on my desktop and debugging on my desktop, it calls into a fake weather sensor. And the fake weather sensor just simply returns some random numbers just to give me some test data so I can play around with my application on the desktop. So I can go ahead and just start that. I'm just going to start the desktop version. So this is just running from my desktop computer, not on the Raspberry Pi right now. And I'll start that up, and you should start seeing up here some random numbers just coming through. It doesn't look really right because, again, they're just random numbers. But this was enough to just debug my application and make sure everything is ready before I wanted to move to the Pi. So got everything working. Then I decided, okay, now I want to create an implementation of the hardware sensor that is actually going to work on the Raspberry Pi. So in this case, this hat has a particular chip on it that is called the LPS22HB chip. And I had to go look at specifications for it and then design this class around it. As I mentioned earlier, it's an I2C interface. There's a great open source project out there called Raspberry IO that is a .NET abstraction on top of a lot of embedded protocols, including I2C. So I utilized that to do the nitty gritty of the I2C communication. And then I implemented the get reading function again, which is going to return, which is basically the idea of this function is it's going to go out, do a sensor reading from the chip, collect the data, and then send it back to the front end to be displayed to the user. Have to do some initialization with the chip. A lot of I2C devices are register based. So the idea is that you have like all these different registers on the chip, and values get populated in the registers, and you just read them at different times to get what you're looking at. So like there's a register called Who Am I, which basically tells you the ID of the chip and whether it's ready to start working. So we go through some initialization, and then I basically tell the chip, hey, I want to start a reading. We'll go look at this real quick. What this is just doing is writing out to a particular register, telling the chip, say, hey, we're going to start a reading. And then, yeah, basically we're going to start a reading, and then we're going to read that value at a later time. The funny thing when working with embedded electronics is things are usually timed. Everything's kind of low level. It's kind of a fun thing and annoying thing. But in this case, there's a specification in the white paper for this chip. Hey, once you start a reading, you just need to wait 300 microseconds before you try to read, or there's not going to be anything there for you to read. The chip actually needs time to go and make the reading. So that's how much time it needs. So just some hard-coded timing there. And then once the reading is over, we basically get 3 bytes back that represent the pressure. And then we put those 3 bytes into this equation that, again, the specifications gave us that basically converted to hectopascal pressure units. And then some similar for the temperature, 2 bytes we get back. And we run through this equation, we get Celsius, and that's how we get the value back. So wrote all this code, but the only way for me to try this now is on the actual Raspberry Pi. So I'll show you how it works, and I'll show you the end result, and then I'll kind of show you how the sausage factory works and how we actually made that work after the fact here. So I'm going to switch the profile here from my local version to this remote .NET Core. So this is basically going to compile the code and deploy it to the Raspberry Pi and then start up a remote debugging session to the Raspberry Pi. So I'll kick that off. And it's going to go do its thing. What it's basically doing is compiling the project for the ARM architecture, and then it's going to use a protocol called rsync to send the files over Wi-Fi to the Raspberry Pi, and then it's going to set up a remote debug session to the Raspberry Pi so I can get remote debugging, and it should be ready at this point. So over here, I'm going to switch from the local host one to the Raspberry Pi one. So this is actually hitting my Raspberry Pi that I just showed you. So it's actually making a Wi-Fi connection to the Raspberry Pi, loading this page from the Raspberry Pi, and then showing the temperatures that's actually reading real time. Temperature and pressure is reading real time from the Raspberry Pi. You might think it's really hot in his room. It's not. The thing about this is the hat is right over the main CPU of the Raspberry Pi, so it's being fed by the Raspberry Pi. But I can show you that, if I spray some air on it, you can watch the values kind of go up and down. Show you that's kind of a real-time reading of the temperature. So one of the great things about this tool, about this setup is, again, remote debugging. So when I was writing this code, it definitely was not a one-time and done kind of code. Again, I was looking through a technical paper, trying to figure everything out, and then trying to translate that into .NET code. And it took a lot of trial and error to get this code working properly. And I needed to be able to inspect the values real time that were coming out of this, and be able to just put a breakpoint here, and then have all the traditional debugging information that you would expect from a .NET application. I can expect all the local values. Again, these are values that have just been read off the Raspberry Pi, not off my local computer. So it's a full remote debugging solution for working with this. So the experience that you expect, you get here is the point. So I was able to inspect all this, debug through it. It really sped up the time with working through the application. So now that I've kind of showed you the end result, let me just give you a little bit of more information about how I set this project up for remote debugging. So in the .vss code folder, there are two files, launch.json and task.json. And here, when I launched this maps to that remote .NET Core launch profile that I use. So when I launch that, it goes through these sequence of steps, which first, compiles and sends the code to the Raspberry Pi. And then here you can see where it's firing up a remote debug session. So I had to install this little program onto the Raspberry Pi called VS Debug, which basically allows a remote debug session to be created on the Raspberry Pi and connected to your code that's running on the Raspberry Pi. So if we go into the task here, you can see the send to Raspberry Pi task. And what this does is first it compiles the code, compiles and publishes the code, and then takes that published file and then uses, as I mentioned, rsync to copy that code to the Raspberry Pi, the new version to that Raspberry Pi, so then it can be remote debugged. So that's the that's the setup process in a nutshell. Like I said, this is all on GitHub. So if you want to do your own .NET Core development of Raspberry Pi, you can kind of use this as a template to get set up and get going. But again, the benefit being that, as a traditional .NET developer, I was just able to use all the same tooling and debugging that I normally would for a full-blown web application or desktop application. I was able to use all the same lessons learned in this environment as well. So let me switch back over to this slide here. Sorry, 1 second. So what else can I do? There was actually an earlier presentation this morning. Someone demonstrating machine learning models on a Raspberry Pi. You can definitely run those machine learning. Here's someone running, I think this is mobile VNet, basically identify this as a coffee mug on the Raspberry Pi. This is, again, a really great edge computing device, because otherwise you'd have to send all the visual data up to a centralized server. You could think of all the bandwidth and latency issues you have there, and then send it back down. Be able to do that on the device definitely saves a lot of processing power. This one, I think, is running at like 4 frames a second. There are manufacturers that make different acceleration chips that you can just plug into the USB port to be able to run models even faster than what the Raspberry Pi can do itself. So that's an option. So that's basically it. I hope that you learned something here. If you're a .NET developer, hope you learned that you could use this platform as a development platform, and learn a little bit about edge computing, and maybe spurred you to try a little bit hardware hacking yourself. And yeah, that's it. So any questions right now? So you have a few questions. Is the code you're showing here going to be available for download? Yes. Yeah, I have a GitHub. So it looks like someone already put the link there for me. So thank you very much for that. Can Aaron use a white background? Black is very hard to see. I'm not going to get into that debate. Can multiple Raspberry Pis be interconnected into a single computing powerhouse device? Yeah, sure. I've seen people build supercomputer clusters out of Raspberry Pis. That's definitely a thing. Am I aware of any good resources to start in on hardware development piece? Yeah, there's a lot of great blogs out there. Like Hackaday comes to my mind as a really good kind of project-based blog that might give you some inspiration about projects you might want to try. Adafruit.com is, they kind of sell hardware projects that you can try, and they do a lot of Raspberry Pi stuff. So you can, for example, build they have a kit where you can build like a handheld gaming unit with a Raspberry Pi. That's a pretty fun project to do if you're starting out. Mike Price said, what other development stacks that are common besides .NET? Yeah, so .NET is not actually the most common development stack on Raspberry Pi. That's kind of why I wanted to do this talk, is because a lot of people don't do .NET development on Raspberry Pi. By far, the most popular development stacks on Raspberry Pi are Python, probably followed up with Java, a lot of Node.js projects, things like that on Raspberry Pi. So Sarah says, in a project, I had to make an Angular application using jQuery library. Page loaded fine on my machine, but on the Pi, it ran extremely slow. Had to adjust all the speed values to remove some animated elements to make it look decent. Is there a way, to speed up this kind of application on the Raspberry Pi? Or is it just limitations of Chromium and Iceweasel browsers? Yeah, I mean, I would say until the Raspberry Pi 4, the Raspberry Pi was not a great desktop user system. It was just a little too slow to run modern web applications. The Raspberry Pi 4, it's probably just now become acceptable for most people. It's still not the fastest, snappiest system. So if you haven't already, upgrade to the Raspberry Pi 4. You definitely get a better experience, end user experience out of that. But to me, I think really the power of the Raspberry Pi in general is for running, server applications. So like running the web server, not so much running a browser, but running the web server that the browser is coming from, or be collecting data or things like that. It's kind of my take. Mike asked how I get debugging to work. It wasn't easy. Went through a few blog sites and tried to piece it together. Like I said, the whole solution is there in GitHub, so you can definitely kind of piece through it and figure out, how I put the debugging solution together. And if you have any questions about it, please feel free to reach out. I'll happily answer those questions. How often do new Pis get released? It seems about once a year or so, and then sometimes they'll release multiple versions. So like the Raspberry Pi 3 has like the Raspberry Pi 3A, the Raspberry 3 Pi B, and then there's compute versions. It really gets crazy because they try to really cover every use case that someone might have for wanting to use these Raspberry Pi. So there's low power versions and faster versions, those kind of things. How differences between the Pi and Arduino? Cameron asked. That's a great question. I have a lot of experience with Arduino-based platforms as well. Arduinos are what's classified as a microcontroller. And Raspberry Pi is, I guess, a full-blown computing platform. So what's the difference? Microcontrollers don't run full OSs. They basically just run your code and nothing else. Where a Raspberry Pi is truly a full-blown multitasking operating system. So it runs full-blown Linux or full-blown Windows with all that overhead and all that capability and flexibility, where Arduino just runs your code, usually very small storage. So we're talking like, 64K storage, just enough to hold your code, nothing more. That's all they do. They tend to be a lot lower power hardware, which is good for some things because sometimes, again, Raspberry Pis are pretty power hungry devices. They use a lot of battery, those kind of things. Maybe you don't need all that. So a microcontroller would be a good use case if you don't need all that. Did I miss any other questions here? Am I using Pi 4 or just Pi 3 units? I did the demo with Pi 4. Like I said, I'm a little bit addicted to buying Raspberry Pis, so I'm usually I have the latest one as soon as it comes out. Yeah, just adding on to microcontrollers a little bit more too. When you need really strict timings and you're interfacing with hardware that's very peculiar about how you interface with it, a lot of hardware like needs to be given commands at very specific timings or tight timings, or readings need to be done in a very precise manner. using a full-blown OS like Linux or Windows, which aren't really real-time OSs, you can really struggle to be able to meet those timing requirements. So sometimes you have to fall back to like a microcontroller that just runs your code, so you can practically dictate when commands are sent out, and interfaces with hardware are very tightly controlled. So that's a use case for microcontrollers too. So we really need tight timing control. So I think we got 5 more minutes, so I'm happy to answer any more questions. What's the most useful application you found on a Raspberry Pi? So I'm really into home automation, smart lights and, smart locks and all those kind of things. Before I was using the Wink platform, which is a commercial closed source platform for being like the hub that controls all your smart devices. If anyone knows anything about Wink, recently the company's been having trouble and they decided to start charging all their users out of blue for using the hardware that you already bought, which originally there's no charge behind it besides just buying the hardware. So when that happened, I decided to abandon that product, and I converted my home automation hub to a Raspberry Pi platform using a software package called Home Assistant, which is an open source package. It basically replaced all the functionality of that hub with something that I have full control over now. I'm not at the mercy of some company deciding to change their pricing model. So that's probably the most useful thing I've done with the Raspberry Pi personally. Yeah, so for a Pi that uses high power, yeah, you can, all the Raspberry Pis just take a 5-volt connection that's typical for like a smartphone charger. And you can power them based off of like, a portable battery that you'd use to charge a smartphone, or you can just plug it right into a power supply that you would charge your phone with. After Pi, what's your next favorite type of Pi? We're talking the food, or Apple would definitely be my next favorite. If we're talking other single board computers, there are lots of other single board computers out there, that aren't, there's the Banana Pi, for example. There's the NVIDIA boards are really cool, like the Jetson, because they have a GPU basically baked in, so you can do AI modeling really fast on those SPCs. You know what? I haven't. That's a great question. I'm probably just going to leave this on, because honestly, this thing has been on all day, and it's not even down to like, it's just like there's a meter on here with 4 lights. It hasn't even gone through gone through one of those lights yet. So it's been on for 8 hours so far, and this is just like a cheapo Amazon battery or phone charger backup battery. So it's been going surprisingly well. Yeah, I don't know how long it will last on this. We're going to find out though.
All right. if you guys don't have any more questions right now, we can let Aaron off the hook for a little bit, but feel free to reach out to him at any time to contact him with questions. I'm sure he'd be happy to answer you. I put a brief feedback survey in the chat. If you guys could please take a moment and give us some feedback on the breakout session so we can continuously improve what we're doing. Aaron, that was an excellent presentation. So thank you so much for sharing with us.
Yes, thank you guys. Thank you for attending. Bye-bye.
All right, thanks everyone.